My name is Rihanna Blount. The date is the 10th of February, 2026.
All right. So we are given the formula C6H12O2. And we first need to figure out what the structure of this formula is going to be. We see that there are two oxygen atoms present. And with these two oxygen atoms, we can assume that they're going to be there's either going to be an ester functional group or a carboxylic acid functional group present. So, in order to determine which functional group we have, we are going to look at the spectrum here. And we see at this obstruction peak here, it is a 1745. So this obstruction peak at 1745, that is going to basically tell us which functional group we have. And according to the table of obstruction peaks, the closest number to that is going to be an ester group. So yeah, we are going to have an ester group present. Regarding the CH bond, we see that the peak is right here below 3,000. So according again to the table of obstruction peaks, that would make that an alkane. So with that being said, we will only have one ester functional group. We can now go down to the table, and we can write in our frequency, which was at 1745. And this is an ester group. All right, you can now look at this carbon-13 NMR spectrum. And the first thing we're going to do in this spectrum is just going to count the peaks. So we see that we have 1, 2, 3, 4, 5 peaks. So 5 peaks is going to mean 5 unique carbons. And also 5 unique carbon environments in the structure. We, in the formula, see that there are 6 carbon atoms, but there are 5 unique carbon atoms. So now we can assume some of the possible structures of esters that are with this formula. All right, so now I'm just going to draw out some of the possible structures for this formula right here. So first structure I'm going to draw. All right, so this structure here is going to represent this formula 6 carbon atoms. 1, 2, 3, 4, 5, 6. It's going to be 12 hydrogen atoms total, and you see the 2 oxygens there. Another formula that we can draw for this for this formula can look something like this. Again, this structure has the same number of carbon, oxygen, and hydrogen atoms as well. 1, 2, 3, 4, 5, 6, 12 hydrogen atoms and 2 oxygens. One more structure that we can draw for this formula. It's going to look something like this. Something like that. And that is going to have the same number of oxygen, hydrogen, and carbon atoms. They all have all these structures do have the same formula, but we're going to find the final structure by looking at the carbon-13 MMR and protein NMR. So now we're going to count the number of unique carbons. So in order to determine which structure is the actual, structure for this formula, include like that adheres to the 5 unique carbon rule that we're going by. We're going to first just count all the carbons, and we're going to look at them in their unique environments. So in this first structure here, we have 1, 2, 3, 4, 5, 6 carbons, which would make this structure not the real structure because we are only looking for 5 unique carbons again. So yeah, premise is 5 unique carbons. That's what we're looking for. The structure has 6, therefore it cannot work. This middle structure here, there's 1, 2, 3, 4, 5 And we're going to count this one as 5 as well because 3 of these are in the same carbon environment. So this one will have 5 unique carbon atoms. So that structure would work. This last structure, we're going to count again. 1, 2, 3, 4. But these ones are going to be 4 as well. So there are only 4 unique carbon atoms in this structure. So this structure is not going to work either. So the real structure in this case is going to be this middle structure right here. Yeah. So now just taking a look at, again, this carbon-13 NMR spectrum here, we see that the peaks here, 1, 2, 3, 5 peaks here. We're just going to start on this end. Looking at these peaks, we see that this first peak is 20. These first 3 peaks actually are between the 20 to 40 ranges. In these ranges can exist a CH3 group, CH2 group, and C tetrahalogen group as well. We can assume that these 3 groups here are all alkyl groups. I'm just going to start looking here at this peak that we have labeled as 1. We can determine by the peak size that it does represent more than 1 carbon atom. So when we look again at our predicted structure, which is the one we decided here in the middle, I'm going to redraw that structure as this. So again, that is our predicted structure. I'm going to go ahead and label these. So these are all the carbons. These are the unique carbons that we have. And this first peak here, first peak we have represented here, that is going to be represented by these 2 5 carbons that we have labeled here on the structure. And the ppm number of those carbons are going to be 19, as it shows here on the chart here. It is at 19, just below 20 for that first peak. So ppm values for these 2 are going to be 19. We're going to go then now to peak number 2. Peak number 2 is at approximately 21 here. So we're going to have that as 21. So peak number 2 is going to correspond with number 4, carbon number 4 we have labeled on this structure. So this ppm number is going to be 21 for carbon number 4. Peak number 3 we see here is at about 28. So we're going to call carbon 3 our, Peak 3 is also going to be carbon 3 in our structure, so that ppm value for carbon 3 is going to be 28 for that carbon in the middle there. And now we're going to look at peak number 4. We haven't discussed much about peak number 4. It has a ppm value of approximately 71. I'm going to call that 71. The carbon atom will be attached to an O in this range, so we can come to our structure here and see that this carbon here is attached to this O. So we're going to call this carbon here, carbon number 1. We're going to say that is represented by peak number 4. So that ppm value is going to be 71 for, 71 for carbon number 1. And finally, we're going to look at peak number 5. This peak does have the largest ppm number. It is between the ranges of 160 and 180. So in this range, we have the carbonyl functional group. The ppm value for this peak is about 171. And this is going to be represented by the carbonyl group in our structure here. So carbon number 2 is going to be peak number 5 with a ppm value of 171. Okay, so that with that being said, we have determined this as a possible structure, but this is not necessarily the final structure. We're going to have to confirm that with the proton NMR. So now we are just going to fill out that 13 carbon NMR little chart here with the corresponding information that we have here. So I'm just going to go ahead and redraw that little structure that we determined could be a possible structure. And that structure is like drawn like this. Okay. Okay. Just redrawing that structure, and then to fill in the table with these ppm values that we have determined down here, we're just going to fill in this table. So first, the first one we found is going to be that 19, that first peak, and that had a 2CH3 groups. And that second peak with the 21 had a CH group. Third peak with 28 ppm value had a CH2 group. CH2, sorry. The fourth peak had a CH3 bonded to oxygen. And then finally, that fifth peak at 171 double bonded to oxygen. So that is for that table. All right, now that we have filled out our 13 carbon NMR chart here, now we're going to again interact. We're going to evaluate this proton NMR chart just to confirm whether or not this is the actual structure. Our predicted structure is the actual structure. So we are just going to draw the expanded version now of our predicted structure. Here, I'm going to draw that down right here. So first we have 2 of these. Make that more clear. And then this one is double bonded to that. Oh. All right. So we see here in this first peak that there is, in this first peak here, the 6H. You can see that there are 2 peaks. The 2 carbon atoms at the end right here. These are signified by this double peak in the 6H. Because there are 6 hydrogen atoms here, this will only approximate to the 1 peak, but because of its neighboring CH right here, we will be able to, it'll be shown here as 2 peaks. Yeah, again, because of that neighboring hydrogen here. So those would be the 2 peaks, and they're both observed below 1 for that value. So that checks out as far as the ppm value goes. But when we keep looking at the rest of our predicted structure, we can see that, so the sum of these 2 are going to be 7. So if we just write it out, the 6 hydrogens from here plus the 1 from here, that's going to give us 7. And if we keep looking here, this 1 plus this one is going to give us the 2. But as we look at this 2H here,
it is at a ppm range of almost 4. In the structure we have that would match, if this was the correct structure here, this ppm value would be closer to this 2.4 range, but it is not. So in this case, we could determine that this is not the correct structure. In this structure, the third carbon here would have to be in that 2 to 2.4 NMR spectrum, ppm value. So if we refer to this table, we can see which functional group should be in the range of around 3.8 where it shows on the spectrum. So, we see that with the atoms that we have, we can use this for reference. This alcohol group here, and this would make sense for what we have on the proton NMR spectrum, and so with this alcohol ether. And yeah, so we see that these groups would work, and these are the groups that we're going to probably need to see in our actual structure. We need to find a structure that would work with a group with either an alcohol group or an alcohol ester group, where an oxygen atom is attached to 2 hydrogen atoms. So maybe a structure like this. That is kind of what we would need to see. So this type of group is possible and would give us a doublet, this right here. So we know that this has to exist in our real structure. So we know that we need this type of group in our final structure. We can now just complete this structure we have by attaching this carbon to 2 hydrogen atoms. This type of group would give us the doublet, so we know that this has to exist. This has to exist in our real structure. And that would bring us into the range of the alcohol ether structure that I mentioned earlier. So now we can rearrange this structure into a structure that would fit the ppm displayed in the structure. The ppm displayed. We can draw a structure that would fit this into it. So I'm just going to draw that down here. All right, this has that group of the carbon attached to these 2 hydrogens and the oxygen. So we can check this out by writing out the expanded formula again to see whether or not this will be our final structure. Attached to C, double bonded to O, bonded to O, bonded to H. Bonded to. So if we compare this now, looking at our proton NMR spectrum again, we can see that this remained the same. These 2, this 6H, this gives us the right range. This structure right here corresponds with these right here, and that will give us that range. And you see that these little peaks, that's the multiplicity. So that checks out. And now this gives us that. This will give us that 3.8 2H ppm. So we know that this now is our actual final structure. Just like that. And with that structure, now we can go ahead and fill in our chart of the proton NMR. The information that we interpreted from the proton NMR. So when we look at our first point, we can call this point here with this, we can call this approximately 9.8. So we will have a chemical shift, 0.98. We will have a chemical shift of 0.98. And we look at our second peak, which is here. We can call this about a 1.8 here for 1H. And the 3H peak is at about 2.2. And the last peak, the 2H peak, is at about a 3.8 there. So we can go ahead and write that chemical shift in there. And so now we can consider integration. So when at 9.8, integration is, 0.98. The integration is at 6. At 1.8, the integration is 1 with only one hydrogen there. At 2.2, integration is 3. And at 3.8, the integration is 2 with 2 hydrogens. That is just corresponding for what we see here in the proton NMR spectrum there. Oh my goodness. Okay, so now we can consider the multiplicity. So when there are 6 hydrogens, there is a doublet, and that is shown again by these 2 peaks right here. And yeah, so we can just fill that chart in where it says multiplicity. We can just write in doublet here. And when we are considering when there was an integration, when there was a 1 integration, we can see there's a multiplet, which means there's many peaks here. So if you look at our proposed structure again, we can see that in accordance with this carbon here, there is 2 carbons attached to here, 2 hydrogens attached to here, 3 hydrogens here as well, and just the 1 hydrogen here. So that would be a total of 9 hydrogens present, but we're just going to write that in as a multiplet. Sorry. So we're just going to write that in as a multiplet. Okay, I don't know why that jumped. At 2.2, the 3 hydrogens would multiplicity, at 2.2, the 3 hydrogens and the multiplicity would be at a singlet here. And the multiplicity at 3.8, where the integration was at a 2, it is going to be a doublet here as well. You can see the 2 peaks, making that a doublet. And as far as the interpretation goes, there are 2 CH3 groups attached to CH. So that just means attached. Don't have enough space, but that's the interpretation for that 0.98 chemical shift. And for the 1.8 chemical shift, The interpretation is going to be that CH bond. For the 2.2 chemical shift, the CH320. Oh my goodness. And for that 3.8 chemical shift, there is going to be a CH2 bond. Okay. So again, that is my proposed structure. Those are my tables and charts there, as we see it from the first. Okay. From the first 13 carbon NMR chart, we had a different structure than what we initially ended up with. So that is why it is useful to use this proton NMR structure. It's not a necessarily straightforward problem to solve here. So luckily with that proton NMR structure, we were able to confirm that we end with the correct proposed structure.